question. Um, okay, this will probably take a long time to discuss this, but a lot of things back here. But let's just try to understand this question with a m equals 30 case. So if m equals 30, basically asking how many numbers n um less than or equal to 30 are there such that 30 divides the summation. Oh, I hate typing on mouse. And to the 9. All right. So you might be thinking, what does it mean for 30 to divide the summation? First, we can re-express this summation as something else, though. This is just equal to a geometric sum of 1 plus n squared all the way to n to the 29, which should just be equal to n to the 30 minus 1 over n minus 1. And it's just asking how many numbers n are there such that 30 divides n to the 30 minus 1 over n minus 1. So let's look at this new sum. We get 30 divides n to the 30 minus 1 over n minus 1, and this implies that 30 divides n to the 30 minus 1. So let's just write that again. And using FLT, if n is co-prime to 30, then n30 should be equal to 130. If n is co-prime to 30, all right? Which means n to the 30 minus 1 should be equivalent to 0, 130. So if n is co-prime to 30, then by FLT, this should satisfy. Is that right? Wait, I legitimately forgot the solution. Oh, yes, yes, yes. It is not mod 30. FLT only works for primes, right?
Yeah, it only works for prime numbers.
Oh, yeah, yeah, sorry, sorry.
Okay.
All right, we're back. I missed a big part of my solution. And using CRT, this basically means that 2, 3, and 5 divide n to the 30 minus 1. So we would have 2 divides n to the 30 minus 1, 3 divides n to the 30 minus 1, and 5 divides n to the 30 minus 1. Wait, sorry, I said that. And actually, this is not true for most n, since by FLT n to the hold on. If you check each case individually, we can see that this works because n minus 1 is equal to 0 mod 2 by FLT for coprime n. N squared minus 1 is equivalent to 0 mod 3 for coprime n. But n to the 4 minus 1 is actually equal to 0 mod 5 by FLT for coprime n. And we realize that n to the 30 minus 1 does not divide n to the 4 minus 1. So actually 30 does not work, I think. Yeah, it shouldn't work. 30 should not work. And so we can kind of check this for other cases. If we just have to check if the totals of the prime factors of the co-prime factors divide the original number. So an example that works would be like 8. And if we do this case for 8 again, we'll have 8 divides n to the 8 minus 1 over n minus 1. And we just have to check the fact that 8 divides n to the 8 minus 1. So that would be Oh, sorry. By by Euler's quotient, we have that the quotient of 8 is 4. So n to the 4 minus 1 should be equal to 0 mod 8 because of Euler's quotient formula. And we realize that the numbers that should work are are the numbers wherein if you get the LCM of the quotients, it divides the original number. Here in 30, the LCM of the quotients is 1, 2, 4 is 4, and 4 does not divide 30, so this does not work for most n. Um, but for 8, the quotient is 4, which divides 8, so this should work for co-prime n. So in general, actually, let's look at the better case. If you look at the case 10, this is asking us if for what numbers of n does n to the 10 minus 1 over n minus 1 divisible by 10, right? Oh, 10 doesn't even work, sorry. Let's do 12. If you look at the m equals 12 case, this is the same question as asking when does 12 divide n to the 12 minus 1 over n minus 1, which is equivalent to asking when does 12 divide n to the 12 minus 1. Not exactly, but we can just look at this right now. And this is the same question as asking when 3 divides n to the 12 minus 1 and 4 divides n to the 12 minus 1. So by FLT, this is true since n squared is equal to 1 mod 3 for coprime n, and n cubed is equal to 1 mod 4 for coprime n. So actually for 12, the numbers that will work are the numbers that are coprime to the numbers that are coprime to 12. So for 12, the n that works should be n equals 1, 5, 7, and 11. So there should be 4 numbers for 12 that work. Is that right? Yes. And realize that this is just equal to um quotient of um quotient of 12. So for numbers wherein the LCM of the quotients divides the original number, the amount of n that satisfy it should just be equal to quotient of 12. So looking at back at the original question, this does not satisfy um the condition that the amount of integers is less than quotient of m. So actually m is a case wherein the amount of n that satisfies it is actually equal to the quotient. An example of a number where this condition is not satisfied is like any prime. For example, we have 11. If you check the number of n less than 11 that satisfy n to the 11 minus 1 equal over n minus 1, the answer should actually be 0 because by FLT, n to the 10 is equal to 1 mod 11 for coprime n. And if you check that, that's obviously not the case. So the condition that we want is for the LCM of the quotients to not divide the original number. And we can just bash this for 1 to 30. For 1 to 30, we want the quotient or the LCM of the quotients to not divide the number. Or we can just count the complementary case actually. The only cases wherein the quotient divides the number are this is pretty known, 2 to the any number of the form 2 to the a then 3 to the b, where a is greater than 1, I think. So all powers of 2 should work. 2, 4, 6, 9, 8, 16. And then Hello, hello. Balik ba ka?
Yeah, we can hear you.
Saglit lang. Alright, sorry, I'm back. Anyway, looking back at the conditions, the only m that shouldn't satisfy it, or the m where the totals the LCM of the totals divide the original sum should be by bashing it should just be 1, 2, 4, 6, 8, 12, 16, 18, 20, and 24. If you realize we excluded all the primes and every other number where the totient does not divide the original, or the LCM of the totals does not divide the original answer. And we realize these are numbers of like, these are powers of 2, like 2 to the A, or 2 to the A times 3 to the B, and 2 to the A times 5 to the C. Because if you realize, if you get the LCM of the quotients, um, these are all, the LCM of the quotients would be of the 4 to the A times 2 to the B times 5 to the C as well. Basically everything, every prime where the quotient is a power. So these should, and actually, all of the numbers here are such numbers. And if we count this, it should be 10, so the answer should be 20. There are 10 numbers where amount of such numbers should be quotient of m. And I just realized explaining this question is not it. I did not provide a solution. That should just be it. You just bash out the numbers wherein the quotient divides the original number.